Okay, Assalamualaikum warahmatullahi wabarakatuh, and good day to all students. So far we have three video lectures that have been given to you, and I'm sure that you have watched the part 1 video, part 2, and part 3. So in part 1, we have completed the basic dimensioning, and part 2, section classifications, and the need of shear buckling check, while part 3 is the shear buckling resistance check. And in part 3, whereby when we have done the shear buckling resistance check, if you realize you have been given examples and also exercise for you to complete for the rest of the plate girder panels. Okay, so basically for this task, it has been completed. So done, done, and done. So now, the last part in our plate girder design is to design the transverse web stiffeners. As we know, in our designs, in these examples, we have a 20-meter span length and we have the panels, but we haven't designed the size of the stiffener itself. In this video, you will learn on how to design the transverse web. Alright, so now let's first look at how can we design the stiffener in the plate girder. So firstly, we refer to our notes. In clause 9.3.3 EC3 part 1.5, equation 5.176, you can see that the force NSRD to be resisted by a stiffener is given by equation in 5.76. So in these equations, NSRD is the force that need to be resisted by the stiffener. Therefore, to calculate this, okay, we need to understand what are the parameters govern the force that need to be resisted by the stiffener. So here you can see check strength of the stiffener, which is taken from equation 5.76. So in here NSRD, we can see what does it mean by NSRD and the rest. So in these equations, you can see that NSRD is the force to be resisted by a stiffener, whereby VED is determined at 0.5 HW from the stiffeners in the panel with the higher shear. Alright, and for this one is the contribution factor from the web to shear buckle resistance of the stiffeners, whereby this value is calculated for the web panel between adjacent stiffener by assuming the stiffener under consideration is removed. Okay, this equation can be found in clause 9.3.3 equation 5.176. Okay, so VED is determined at 0.5 HW, which is the height of web, from the stiffener in the panel with a high shear. So what does this VED means? Okay, so refer back to our questions, okay, whereby you can see we have those panels. Panel A, B, C, D, E, and F. So now we are designing these panels and we are looking for the first stiffener, which is stiffener at position B, the transverse web stiffener here. So this stiffener is at 1.2 meter. So I enlarge this stiffener and it become like this. Okay, that it is become like this. So here you can see the distance is 1.2 meter. And this is the load applied on top of the plate girder, which is 232 kilonewton per meter. And the 0.H5 from the stiffener in the panel with the high shear means if you're designing these panels, so you need to calculate this VED at 0.5 HW from the panel that you are designing now. So here, the panel that you design is panel AB, 0.5 HW. What does it mean by HW? HW is the height of the web. So in this case, you are need to calculate the VED at that particular point. So, for example, in this case, okay, for panel AB, where you are now designing what is the size of this panel, which is this transverse web, I mean. So the shear force is 2320. The length is 1.2 meter. So because we need to measure 0.5 from 0.5 HW from the transverse web stiffener, therefore the remaining length from the 2320 is 1.2 minus 0.5 HW. To calculate the VED here, okay, you can see VED is equivalent to 3220 going upward minus 232 kilonewton per meter times with this distance, whereby 1.2 minus 0.5 HW. So 1.2 minus 0.5 HW is 1930, and you finally calculated it and get 2265 kilonewton for the VED. So by now, you have calculated VED and you got it as 2265 kilonewton. Let's find the contribution factor. So as I said earlier, the contribution factor from the web, okay, to shear buckle resistance of the stiffener, whereby this value is calculated for the web panel, which we're going to design, which is panel AB, which is at the stiffener B, assuming the stiffener under consideration is removed. Okay, so before I show you how to do this, let's look at the notes, whereby in clause 5.3, you can see that clause 5.3 EC3 part 153. The slenderness parameters, table 5.1 and figure 5.2 should be taken as as you can see in equation 5.3, and the value of the parameter can be found in 5.4. However, in our case, we are now design a stiffener. So instead of using 5.3 as what we checked in the shear buckling resistance earlier, we are now looking at the options that we have here. So if you can see, we have equation 5.5 and equation 5.6, whereby in equation 5.5, the slenderness parameter is for when you design a transverse stiffness, whereby it's only have at support. And B is a transverse stiffener at supports and intermediate transverse stiffness or longitudinal stiffness or both. So in our case, we are using equation 5.6 because if you can see in our plate girder, okay, we have so many panels in the intermediate span, whereby these are the panels. If you are choosing equation 5.5, it means that you only have a panel at supports, whereby you don't have all the rest of the panels. Okay, so if you're looking at the equations given, so definitely in our case, we are using equation 5.6 from clause EC3, part 1.5, equation 5.6, whereby the slenderness parameter is given by these equations, because the transverse stiffener at supports and at intermediate transverse web throughout the plate girder. So now we wanted to know what is this parameter. In looking at this, we know that we already know what is our HW, which is 1930, and we need to find this first. So in that parameter, okay, to calculate that, therefore you have to look at EC3 Part 15 clause 5.12. In this box, you can see that you need to know what is your A over HW. Is that either larger than 1 or lesser than 1? Because from there you wanted to choose which equation is suitable for your conditions. Okay, so now let's find this value, whereby to calculate the contribution factor, we need to assume that the transverse stiffener in which we are designing now is considered to be removed. So if you look here, okay, if you look here, here are the panels that we designed, where we have A, B, C, and D. So these are the panels that we are designing now. Panel B. So as we wanted to calculate the contribution factor, okay, so the contribution parameter by assuming that the absence of the panel. So we need to take out the panel, remove the panel B, the one that we are designing now, by having this. By remove the panel B, we are now having the distance of 2.55 meter, which is panel A and C. So for you to calculate the value of A, which is A over HW, which is referred to clause 5.12 EC3 part 15, the A here, when you design the stiffener, is given as 2.55 meter. So then you get A over HW, which is 1.3 to 1, and HW over A is equivalent to 0.757. Insert in these equations, finally you get 7.63. So you have to make a note there, note, for a transverse web stiffener design, transverse web stiffeners designed XW, or the contribution factor, is measured by assuming that the stiffener that we designed, the stiffener that we going to design, the design is removed. Okay? Okay. Now, since we already have this value, which is 7.63, so we are now able to get the value of the slenderness parameter, which is 2.55. So again, as we have been carried out in shear buckling resistance checks, so then you go for table 5.1, clause EC3 part 15, to check which conditions is suits for your lambda. So in these conditions, your lambda 2.55 is larger than 1.08. Therefore, in your equations, for the non-rigid end post, you need to use the criteria number 3 in the row 3. So then you get, when you insert the value, lambda W 2.55, then you finally calculate it by having the contribution factor is 0.325. And lastly, okay, what you need to do, by having those all the parameter required, you can then substitute again in the main equations, whereby you wanted to find what is the design force that should be resisted by the stiffener. So the design force that should be resisted by the stiffener is 1108 kilonewton, which is lesser than 2042 kilonewton, where 2024 kilonewton is measured. This is A, this is B, is measured at the shear force directly at the panel B. So since the design stiffener is lesser than the shear force at B, therefore the transverse stiffener, the design force of the transverse stiffener is satisfied. We now know what is the load that should be carried by stiffener B. Okay, so imagine this is stiffener B. Okay, imagine this is stiffener B. So we are now know that the here we have 232 kilonewton per meter, and then the load that should be carried at point B, okay, for stiffener B, which is calculated previously in NSRD, okay, which is 110.8 kilonewton. So we are now know that the stiffener B should be able, the design load for stiffener B is 1108 kilonewton. Okay, so by knowing this value 1108 kilonewton, and we also know that the shear at that particular point is 2042 kilonewton. So the next step is that we need to understand, we need to design the size of the stiffener. So if you look here, this is the plate girder, okay, and we have the stiffener here. So we know that the load that should be carried by the stiffener is 1108 kilonewton, but we still do not know what is the size of this stiffener. So the next step is we need to design the transverse web stiffener at A and B. Okay, and B. So to do this, you need to refer to our slides or our notes that we have simplified for you. All right, you can see clause 9.33 EC3 part 1.5, okay, whereby in that clause it provides the minimum second moment of area. Similar to the beam, okay, similar to the beam, when you wanted to calculate, to propose a design, you will use whereby MPLRD is equivalent to WPL Fy over gamma m naught, isn't it? So this you use to determine the size of beams, whereby when you rearrange these equations, you will have MPLRD gamma m naught over Fy, and then you will find what is your plastic modulus. Okay, your plastic modulus, which is the second moment of area. So you can refer to equation 5.179. So this is equation 5.179, and this is equation 5.180. Okay, so you need to refer to equation 1.579 and 1.80. So first you need to check the conditions whether A over HW is lesser than square root 2, and then you can use equation 5.179. But if your A over HW is larger than square root 2, then your second moment of area is given as 0.75 HWT cubed, which is given in equation 5.80. So from that equation, okay, what you need to do, to determine the size of the transverse web stiffeners, you need to rearrange the equations. Okay, you need to rearrange the equations. So you know that the second moment of area for a rectangular size is BT cubed over 12. So because your stiffener is rectangular, okay, so rearrange these equations. So then you will get square root cube 12I over T equals to B. And in this case, you assume T is your equivalent to thickness of web, whereby earlier you are assuming that your thickness is 9. So in this case, for you to propose the section sizes of the stiffener, you can again assume that the T of your stiffener is equivalent to the size of the thickness of the web. Okay, as has been mentioned earlier, to propose the size of intermediate transverse web stiffener, okay, first we need to check either our A over HW is larger or lesser than square root 2. So then we now calculate A over HW, which is A is the distance, in this case is the distance from the support to the web stiffener, whereby you can have A over HW 1200 over the height of web, which is 1930. You get 0.62, which is lesser than square root 2. So when you get that, okay, does the IST value, okay, if you look here, IST value is equivalent to equations 5.179 because it complies with these equations. So insert all the parameters, okay, in the equations. T for the stiffness web, you are now again, I highlight, you assume it is similarly, or you propose it to be similar with the thickness of the web. Then finally you get this value for IST, 546 times 10 to the power of 6. Okay, so now you already have the value for your second moment of area for the stiffness. So this value you insert back in the equations which has been calculated earlier, we show you, whereby you have this value. You rearrange and you can now get what is your B, because your T is similar with the thickness of web. So then finally you insert back in the equations and you remain B as unknown. T is equivalent to your thickness of web. So rearrange, you get B equivalent to 194 mm. So in these examples, we try to propose the B, which is the width of the stiffener, is 200 mm. So basically, the stiffener size that we propose at B is 9 mm, which is the design thickness 9 mm, and the width is 200 mm. Okay, so once we know the size of our stiffener, so then we need to determine what is the capacity of the stiffener itself. This particular case, we propose to have two sides of stiffness, which means this is the plate girder. So we propose to have the stiffness at both sides of the plate girder. So in order to find what is the capacity that need to be carried, that is able to carry by this size of the plate girder stiffness that we propose, we refer to clause 6.24 EC3 part 11. So in this clause 6.24 EC3 part 11, we have the equation whereby NRD is equivalent to AS/FYS over gamma M naught. So therefore, NRD is given by 2, because we have two stiffness, times with the capacity required by the stiffener, which is FYS over gamma M naught, taken from clause 6.24, and insert the equations, and finally we have 1278 kilonewton. Okay, so once we now know the resistance capacity of the stiffener is limited to 1278 kilonewton. So now we wanted to see whether this stiffener will buckle under the resistance force that we have applied, that we have calculated earlier. So then we need to check the capability of this stiffener towards buckling. So to check the buckling resistance of the proposed stiffener, you need to go to clause 6.3.1, which is in EN 1993 part 1.1. Okay, so first thing you have to check whether your slenderness parameter is lesser than or equals to 0.2 or NED over NCR lesser than 0.04. If lambda is lesser than 0.2, thus the strut buckling resistance check, you don't need to conduct it. Whereby if NED over NCR is lesser than 0.04, the same thing whereby buckling effect may be ignored. So in clause 6.3.1, you can see that lambda is equivalent to A equivalent Fy over NCR. So what are those parameters? You look here that I have been simplified for you. Okay, I have simplified for you. A equivalence is carried out. You can look at clause 9.3, EC3.15. For a symmetry stiffener, the effective area AE is given by these equations, whereby you can get it from equation 5177. AST is the area of stiffener. Let me show you the slides in our notes. Okay, and what does it mean by L? L is the effective length, which is taken as 0.5 HW. Okay, and this can be referred to the notes that we have in our class. So here are the notes which referring to this statement. And IST is the second moment of area of the stiffener, the one that we have calculated earlier. And these equations you can get from equation 5.178, which is in these slides. So our job now is to calculate, to check whether the buckling resistance of the stiffener need to be carried out or not, by referring to the size that we proposed earlier. So we need to check whether lambda is lesser than 0.2, or we can use NED over NCR less than 0.04. In this case, we use lambda, in which this is the equations. So to do that, as we know, all the parameters that need to be carried out. So here we determine the A equivalence. So we have calculated the A equivalence. This is the area of the stiffener. Why 2? Because we have two sides of the stiffener as proposed earlier. And we get our A equivalence equals to 5577 millimeter squared. And determine the I equivalence, okay, because in earlier we need to find what is our I equivalence. So I equivalence, so then we have, this is the stiffener, 400 T thickness. So we use these equations. IST we calculated earlier, okay, 409, and then we know that it is actually BH cubed over 12. So then you insert the equations here, and finally you get the I equivalent equal to 48.0 times 10 to the power of 6 millimeters squared. And then in these equations, you also need to find what is your NCR. Okay, so NCR is being calculated as you can see here. NCR is given by pi squared EI equivalent over L squared. You know what is your I equivalent because you have calculated before. And then L is taken as 0.75 HW, this value. Finally, you get 47462 for NCR. So once you get all this, you now can solve these equations by inserting the A equivalents, Fy and NCR. Finally, you got this. A equivalent, which has been carried out earlier, 5577, times with Fy over your NCR, and you get 0.204, which is lesser than equal to 0.2. Thus, in this particular case, with the minimum size thickness that we have here, we can assume that our buckling is satisfied. Okay? Because we are choosing at the minimum stiffness. So, therefore, the minimum stiffness size will be adequate for all intermediate stiffness. Meaning that in this particular case, we can say that the size that we propose for this stiffener, okay, that stiffener for panel AB, which is 200 T, okay, 9 mm, is satisfied for all intermediate stiffness. So you can apply the same size for B, C, D, E, and F. Okay? Okay, so now we know that all the intermediate stiffness, the size which is satisfied is 200 mm width and 9 mm thickness. So, for all stiffness, usually we do require the end stiffener to support the high shear at this particular support. So, now the next step is to design the end stiffener. Okay, so similar like we have done earlier, whereby we designed for the intermediate transverse web stiffener. So now we are designing for the end stiffener. And end stiffener usually will come out with a bigger size than intermediate stiffener because the end stiffener is the place whereby the high shear load will occur. Okay, the high shear load will occur at the end of the stiffener. And therefore, it will carry the high, therefore you need to come up with the thicker transverse web at that particular stiffness, which is at location A. So in this case, okay, you can see that the end stiffener, for the end stiffener, okay, we are now proposed to have 500 mm width and 15 millimeter thick. Okay, so there is a clause saying in EC3 part 5, for end stiffener, you need to take into consideration about 15 strain T portions of web into account for in calculating the effective area of the end stiffener. So meaning that you have the length of the web that you need to take into consideration is 15 strain T, whereby you get 110 mm. Therefore, the area of the effective stiffener at the end of your end stiffener, is equivalent to area of stiffener itself, which is 15 millimeter thick, 500, plus with the portions area of the web, okay? Plus with the portion area of the web. Similar goes for the second moment of area for the stiffener, whereby you have IS. You need to calculate what is the second moment of area for this particular size, 15 mm thick, 500 mm, and height is 1930. Okay, so how we can determine ASEFF, which is equivalent to area of stiffener plus area of the web, which is in end stiffener, we need to take into consideration an effective area or effective length of the web. So here you can see ASEFF is equivalent to area of stiffener 500 times 15, this area 500 times 15, plus 110 times 9. So why 110? Here, because the length of the web is 110 and 9 is the thickness of the web. So you get 8490. And effective second moment of area is calculated by having second moment of area of the stiffener plus a portion of the web. A portion of the web again, I remind, which is here. We need to consider when we design the end stiffener. So then finally you get 0.156 times 10 to the power of 9 millimeter squared. Sorry, millimeter to the power of 4. So again, similar to the intermediate stiffener, once we propose the section sizes, we then need to follow up with the buckling check, whether or not we need to conduct the buckling check of the stiffener. Because we don't want to have whereby we provide the buckling stiffness and at the end, the stiffener itself is buckled. You need to bear in mind that the presence of the stiffness in the plate girder, the function is to help the web in carrying out the axial or the shear force getting from the flange or applied from the load. So in this particular case, again, similar, we repeat the same process whereby we now need to check whether the stiffness that we propose at the end of the plate girder with the size of 500 mm times 15 mm is satisfied or not, or do or not we need to conduct for the shear buckling resistance check. So we then again conduct the same check and we need to find what is our lambda, slenderness parameters. Again, we need to find what is NCR. So here we have NCR, which is pi squared EI over L squared. Again, L is equivalent to 0.7 HW. Include all the parameters necessary requires in these equations. Then you get 154,210 kilonewton. So I is taking as IS over AS because I is the radius of gyrations. Okay, I is radius of gyrations, where this equation can be get from EC3 part 1 okay, in resisting the compression force towards buckling. So I equivalent to IS EFF, which is the one that we calculated earlier, IS EFF and ASEFF we have calculated earlier. So here you get 0.1568490. Substitute in the lambda all the parameters required. Finally, you get 0.14 less than 0.2. So it shows that your lambda is 0.2, then it's okay. All right. Okay, next we wanted to check whether the proposed stiffness, okay, what is the capacity of the force of the proposed stiffness? And this has been carried out as well in the intermediate stiffener. So the NRD, okay, for the proposed stiffness. So we have A here is the A equivalence, 8490, including the area of web. So here A is the area stiffener plus a portion of area web. So you have 8490. You get lastly 3014. Whereby if you can see here, the 3014 kilonewton is larger than the reaction force of your structure. If you look here, the reaction force that you determined earlier here is 2320 kilonewtons. So the shear force here 2320 kilonewtons, and those force the capacity of the stiffener itself is larger than the force, which is 2320, which means it's okay. All right, because we cannot have the reaction force is larger than the capacity. We always have to make sure that the capacity, which is nRD A Fy over gamma m0, must be larger than the reaction force that we design for the plate girder. So in our case, it is satisfied. So once everything has satisfied, one more last check that we need to conduct is to check the resistance of the stiffener towards lateral torsional buckling. So we wanted to make sure that our plate girder does not buckle laterally and torsionally under the applied load. So how can you ensure that? So in order to make sure that our plate girder that we propose are not experiencing lateral torsional buckling, you have to go to class 9.2.1, EC3 part 15, equation 5.172. So in these equations, you will find these equations, whereby this is the Saint Venant torsional constants for the stiffener, and this is the polar second moment of area about the edge fixed to the plate, and it has to be larger than 5.3 Fy over E. So if this is satisfied, then it means that your plate girder will not susceptible to lateral torsional buckling. So let me show you the slide which indicate this. So here are the slides that indicate those equations. All right. So what is IP? IP is equivalent to second moment of area about x-axis plus second moment of area about y-axis. You know that second moment of area for the rectangular is BH cubed over 12. And if y, you have B3, B cubed H over 12. Substitute the equations because you know the size of your stiffener and stiffener. Then you get 0.157 for your IP. And to get the Saint Venant equations, which is IT, you can get these equations from textbooks, which is given by HB cubed over 3. So you get these equations. So finally, you can calculate whether IT over IP is larger than 5.3 Fy over E or it is lesser than it. Okay, so once you get all those two, you substitute into the equations. You found out that Fy over E is 8.96 times 10 to the power of negative 3. You found out that IT over IP is not larger than 5.3 over 5.3 Fy over E. So in this particular case, it seems like by having those transverse web stiffener at the end or on top of the support reactions is not enough. Therefore, we are then suggest that you need to propose a thicker end plate to avoid the lateral torsional buckling at the end of your stiffener. So this is the end of the stiffener. The size that we proposed earlier is not enough. So you may need to provide a thicker size. So we propose to have 25 millimeter. So once you have proposed the 25 millimeter, the same check need to goes again, and I'm sure it is enough. Okay, you can check and to see whether it is enough or not. And finally, you need to check the flange to web welds. You can refer to this clause, which is on the last page of our notes, and it has to satisfy with this. But in these equations, the weld between the web flange should be designed for a shear flow, okay, VED over HW. But if the condition in equation 5.181 is not satisfied, the weld should be designed under a shear flow of these equations. So in our case, we have designed it into these equations, and it is satisfied.
Alright class, exercise 2 is given here, to enhance your understanding on this topic. Answer all questions, and in our next class, you are required to present the outcome during the Google Meet session. Good luck.